right, so today we're going to continue our discussion about the convergence or asymptotics of those transformed random variables. So we presented the basic theorem called the Crammers Theorem, also known as delta method, for deriving the asymptotic distribution of a transformed random variable sequence. So in detail, it's here. This is the major result of Cramer's theorem. So we look at this general form. So we have this convergence of xn in law, right? This is about asymptotic distribution of root n times xn minus its mean mu. Then what we do is that we apply a transformation or function g to xn, and we are interested in its asymptotics. So this Cramer's theorem gives us a very clean result. It basically says that you just need to scale the random variable in the limit, and the scaling factor only depends on the first order derivative of g, and you evaluate this derivative at mu, the mean. So it's a very clean and simple result. So specifically, as in most cases, this condition was derived from central limit theorem. Like here, then the x will be a normal random variable. And then after the scaling, the scaling factor enters the covariance matrix or variance if it's one-dimensional in the normal distribution. So you still have a normal, but you just need to modify the covariance matrix by multiplying the derivative evaluated mu for twice. So in the matrix form, it's a left and right multiplication. That's it. However, we notice that in some cases, we may have an issue. So this is an example where we do have an issue. So it's here, actually, it's here. So in this example one, we are interested in deriving the asymptotic distribution of sample mean square. And by Cramer's theorem, we found that the variance, asymptotic variance, involves mu. So when mu is zero, the variance becomes zero. So we have a degenerative limiting distribution, which becomes the point mass at zero. And this is not useful. So in this case, we need to multiply the left-hand side by a larger constant, larger than root n, increasing faster than root n does, and that's n. And here we found that using this, we can have a non-degenerative limiting distribution that becomes a scaled chi-square 1 random variable. So this is a special case where we showed, okay, if we have this first order approximation, because the Cramer's theorem, you see, in the proof, we are basically using the mean value theorem. That's a first order linear approximation. If this does not work well, then we need to go to the second order. And here is what we stopped next, where we stopped next last time. So improve the approximation. So still following the idea of Cramer's theorem, what we do is that, you see, we go another term into the second derivative. And with the second derivative, we have a quadratic term out here. And then what we can do is that we combine them into a quadratic term. So here we are using this thing, which is called we introduced in the first class, it's the asymptotic equivalence. The reason we can do that is because in most cases, right, this is not obvious because we're not introducing n here, but in most cases, if it's xn, right, xn bar, that's the average xn bar here, then you will have constant 1 over n squared out here, and further terms will have 1 over n cubic. So you see that these terms become smaller and smaller as n goes large. So that's why here we can have this approximation. And furthermore, you see, in this case, it's very interesting that once we do the combination, we would be able to say, coming here. So we would be able to use this formula which is right here. And what's interesting about this is that if we consider this as a constant, it is a constant, right? Root n times g prime mu over sigma times g double prime mu. We call this a constant gamma n. Then you see this thing, this ratio by the central limit theorem, if this one is standard normal, right? So let me just write it down. Probably I should add bar to avoid confusion. Yeah, I should add this bar here. So let me continue. So by central limit theorem, we have root n xn bar minus mu over sigma convert in law to standard normal, right? So now this should be something we're already very familiar with. Then you see, what we have here is that we are basically shifting this by gamma n. So we're shifting its center, we're shifting its center from 0 to negative gamma n. That's the new center for this. The center is gamma, not negative gamma. We're shifting the center for this from 0 to gamma n, and then we take the square. And so the distribution of this actually has a name. So let's say that we define a notation, let Z be standard normal. Okay, then the distribution of Z plus gamma n squared, we give this a name. We call this a non-central chi-square distribution, and we give it a name, chi-square 1 degrees of freedom with shift gamma n. So this is called a non-central chi-square 1. Okay, and then furthermore, here we subtract this gamma n. So that means that after we obtain this random variable here, we further shift it by gamma n squared. So we would have what? So we can say that this as, so it's like Z plus gamma n squared. This is a random variable and we shift it by a constant. So in other words, you see that after all these arguments, we can actually say n times g xn bar minus g mu converge in law to sigma squared g double prime mu over 2. And the distribution can be written as chi-square 1 shifted by gamma m and then minus gamma n squared. Okay, so you see now the asymptotic distribution has a constant n here instead of root n. So then you may wonder, a natural question is, why do we have two things, right? The Crammers theorem tell me one thing, and here you're telling me another thing. And I think a reason why this is not contradictory to Cramer's theorem, so this is a question. Does it contradict the Cramer's theorem? You can think about this question. And here I want to say that the answer is no. The reason is what? The reason is that it depends on this gamma n. This is so important. So one thing that is very interesting is that we actually have a very interesting fact. Okay, I would say the answer is no. So a very interesting fact is this. The distribution chi-square 1 with center gamma n, okay, shifted by gamma n, and minus gamma n squared. This is very close asymptotically close to, or maybe I can write it this. So it's actually asymptotically equivalent to normal distribution with mean 0 and variance 4 times gamma n squared. This is a very interesting fact when gamma n is large. So you see gamma n here involves root n inside here. So you can see that if this g prime mu is fixed and g double prime mu, so we can safely assume that they are both unrelated to n, right? So constant, constant, constant. And the only thing that's changing is root n, and root n is part of gamma n. So you can imagine that gamma n is actually increasing. So when gamma n is very large, then these two distributions are actually getting closer and closer to each other. And that's a very interesting fact. So one thing you could check is that on your computer, you can plot the density for left-hand side, the non-central chi-square distribution, and then do a shift. And you can exactly see that it looks very like Gaussian when this gamma n is very big. So you can see, I can see under what case would gamma n be not large? Looking at the formula of gamma n. When g prime mu is equal to 0, right? When it's equal to 0, you stay at 0. And then that will be the case. Okay, let me say when gamma is up. So if g prime mu and it's not 0 and g double prime mu is not 0, right? If g double prime mu is 0, gamma n will not exist. So we cannot discuss it anyway. But if g prime mu is not 0, g double prime mu is not 0, then this gamma n will increase with n for sure. And that's the case when gamma n is large. But if g prime mu is 0, then we would have gamma n equal to 0, right? And when gamma n equal to 0, we are under what case? We would have root n g x n bar minus g mu converge in law to sigma squared g double prime mu over 2 times chi-square. And this is just a standard chi-square. There's no shift. And this is exactly the case where we saw in that example 1. This example is this case. So this is exactly the case where we saw here about the distribution of x n bar square. Okay, so you see that in this case, we have to use this distribution instead of this distribution because this normal distribution would have 0 mean, a 0 variance, and that's not usable. And this one is okay, but you know, this one, root n g x n bar minus g mu, convergent law to normal 0 for this one is not useful because it becomes degenerate. It's just 0. So you see the case where we want to apply this second, my bad. So this is a typo. This one is n. Yeah. This one is n, this one is root n. So the case where we want to apply this top one is when the gamma n is 0. And that's often the case g prime mu evaluated at mu is 0. Right? That's the case where this lower one, this asymptotic normal one cannot be used. So we have to use this chi-square one. So this is a general discussion that generalizes the case we saw in example 1. Okay, so let's continue. We're going to discuss a very, very important application of the Crammers Theorem and the functions of sample moments. So here we're going to discuss the asymptotic distribution of the Pearson correlation, sample Pearson correlation. Asymptotics of sample Pearson correlation. So in many cases, if you don't hear, if it's not specified which correlation it is Pearson correlation. So if people say sample correlation coefficient, they meant the Pearson correlation. Okay, so in this case, we have a sample of size n, right? And we call our sample, we denote our sample as x1, y1, x2, y2, 2xn, yn. So it's n pairs of random variables, one-dimensional. Okay, so xi, yi are one-dimensional. And what is the formula of their Pearson correlation, sample Pearson correlation? So let's first introduce a few notations. So the first notation is at the sample level, and the second set of notations is at the population level. So we define the following notations. Sx squared is the sample variance of x1 to xn. So in this case, it does not matter whether we use 1 over n or 1 over n minus 1, because they will be canceled anyway. But let's just use 1 over n minus 1, because that's something you're more from. Oh, let's just use 1 over n. Yeah, that's easier. 1 over n, and I go from 1 to n, xi minus xn bar squared. Okay, this is the sample variance of x1 to xn. And similarly, we define as y squared yi minus yn bar squared. So this is the sample variance of x1 of y1 to yn. And we have the sample covariance, which we write as sxy. So here it's defined as 1 over n. Okay, it's xi minus xn bar, yi minus yn bar. And we call the sample covariance. Covariance of the pairs, right? So the x1, y1 to xn, yn. Okay, so we have the sample variances and sample covariance. Then what is the sample correlation? The sample correlation or sample Pearson correlation, we use notation R. Then this is defined as Sxy divided by Sx times Sy. So there's no more square. Basically, we take the square root of sample variance, multiply it by the square root of sample variance of y. So that will be the denominator, and the numerator is the sample covariance. Okay, so these are the sample level statistics. Sample level statistics. And correspondingly, we can have their population version. So the first notation, we call it sigma x squared. And this is defined as the expectation of xi minus mu squared. Okay, because the xi's are IID, then I can replace xi by x1. It doesn't change the meaning. So this is the variance of xi, the population version. Similarly, we have sigma y squared. Yi minus, oh sorry, I should mark mu x to mean that it's the mean of x. Yi minus mu y This is the variance of yi. And we need a covariance. Here, we use notation sigma xy. So that's defined as the expectation of xi minus mu x times yi minus mu y. And that's the covariance of xi in yi, right? So then finally, we can define the Pearson correlation. Here we use the notation rho. That's defined as sigma xy divided by sigma x times sigma y. So same idea, but the sample statistics are replaced by population parameters. So these are what we call population level parameters. Okay. Then what we're mostly interested in is the asymptotic distribution of R. How would the distribution of my sample level correlation looks like? How will it concentrated around the population correlation? That's my question. Okay, so the question here is, I'm interested in, the question is the asymptotic distribution of R. That's the question. And now you see this derivation gave us a foundation for the derivation. The reason we can do it is because with this derivation, we have expressed R in terms of Sxy, Sx, and Sy. Each of them is a sample moment. And as we know, sample moment, we can derive their asymptotic distributions based on Crammers Theorem and also central limit theorem. So those two things allow us to actually derive what is the Sxy's asymptotic distribution, what is Sx squared, what is Sy squared's asymptotic distribution. And here I need their joint distributions. But that's not too difficult because they are functions of sample moments. So you see, what's very interesting here is that I can further write those as, so once I'm going to write it down, but I'm going to say it first. So this one can be expressed as the average of xi squared minus the square of x and bar, right? So then you see it's a function of those two things. And based on what we have seen before in example 3, which I'm going to pull here, in here. So you see, this is what we did last time, example 3. So this Sn squared is like our Sx squared over there, can be written as the average of xi squared minus the square of x and bar. So you see, this is what we did, right? We apply Cramer's theorem, we have applied central limit theorem, and then Cramer's theorem, and then we can derive the asymptotic distribution of Sn squared as this. And we can do that. So this result can be applied to derive the distribution of Sx squared, Sy squared, and Sxy. So we need to do that jointly. And then we just apply Cramer's theorem once again to combine Sx squared, Sy squared, Sxy into a function that will be the sample correlation. And then we will derive the correlations asymptotic distribution. So that's the whole idea. But let's go one step further to write it down. So to help you understand, I'm going to introduce those notations. So here, what I'm going to do is that I will, so basically, so what I want to say is that if I denote using the moments, okay, I call it mx equals 1 over n summation xi. And I call mxx as 1 over n summation xi squared. And you see by this way, I can also have my 1 over n summation yi, myy 1 over n summation yi squared. And then finally, I can have mxy as 1 over n summation xi yi. So I introduce those moments. Then you see, I can actually derive the joint distribution of these things by central limit theorem. Okay, so you see, I would be able to by CLT, I could derive what we have the asymptotic normality of what? Of root n times this long vector mx, my, mxx, myy, and mxy. So I can have this vector, which are all means, sample means, and then minus their respective expectation. So this one will be equal to mu x, right? And this will be mu y, right? And this one is actually the expectation of the square. Expectation of the square is equal to mean square plus variance. So it's actually equal to mu x squared plus sigma x squared. And expectation of this is mu y squared plus sigma y squared. And what else? The last one, right? This one is equal to covariance plus the product of the mean. So this is mu x mu y plus sigma xy, the covariance. Okay, that's their mean. And these 5 things will converge in law to a 5-dimensional normal distribution. So the mean is 0, 5. And the covariance matrix will be a 5 by 5 covariance matrix. So essentially, we can write it out. And in terms of what? In terms of these things. So that's actually implied in the central limit theorem. So maybe I can just briefly write it out. So this is a 5 by 5 covariance matrix, right? And so in the first term, it will be the variance of x itself. So that's sigma x squared. That's not a problem. Second diagonal, sigma y squared. Okay, this one is a little complicated. It's actually the variance of xi squared, variance of yi squared, and variance of xi yi. Okay, that's the variance term. And so for each one, we will have a covariance. Like here, we would be sigma xy. But down here, we're going to have some covariance. So I'll just leave it here, some covariance and some covariance. So covariance needs to be calculated. That's the complicated matrix, this 5 by 5 covariance matrix. But now we can actually combine these by the Crammers theorem by applying Crammers theorem, we would be able to derive the asymptotic distribution of sx squared sxy sy squared minus their mean. Here, their means are sigma x squared, sigma xy, sigma y squared into something normal. And this normal is 3-dimensional, okay? But there needs to be a covariance 3 by 3 covariance matrix here. So here we can apply Crammers theorem because of a very natural result. Because we have Sx squared equal to mxx minus mx squared. That's a fact. So that's why this thing is a combination of these two. And sy squared is equal to myy minus my squared. And sxy is equal to mxy minus mx times my. So because of this relationship, by the similar argument as in our example 3, we could derive this. Then with this, we apply Crammers theorem once again, to convert this into our R. So that will give me the asymptotic normal distribution of the sample Pearson correlation minus the population Pearson correlation. And this will converge to normal distribution with mean 0. And here I also have a covariance, so I have a variance term. And the variance term is denoted by gamma squared. That's one dimensional. So it's actually depending on that transformation, right? If you assume a function g such that R is equal to a function of sx squared, xxy, sy squared, because of this relationship, then given that function g, you can find its derivative and evaluate the derivative at these values. And that derivative, by our definition, is a row vector. So you have 1 by 3 times the 3 by 3 matrix times the 3 by 1 vector. That will give you a scalar. That's how we get here. Okay, so here you see the whole logic, and what's remaining is just algebra. So there's a lot of calculation involved. And for this type of problem, I will strongly encourage you to actually, I don't know how many of you know that, but there's a software called Mathematica that's specific for this type of job. So they can do symbolic computation. And it's the very nice thing, symbolic computation, which means that you don't need to supply numbers. You just supply symbols and they can do the algebra. But what's very nice here is that I think R now has an interface for doing that. So even though you don't have the software Mathematica, you can do it in R. So this is the whole story. And what's very nice, I think, is that we can derive the asymptotic distribution by using Cramer's theorem for twice. And what's more here is the gamma, right? What is the form of the gamma? The form of the gamma is a little complicated, but if we really look at it, it's not that unreasonable. So let's just try to write it out. So the gamma has this form. So it's 1 over 4 rho squared. Rho is the population Pearson correlation. Multiply by this term. I'm going to define it later. So, but I'm going to write it down first. We call Cxxxx over sigma x fourth. So that's the x variance square plus 2 Cxxyy sigma x squared sigma y squared plus Cyyyy sigma y fourth minus rho Cxxxy sigma x cubic sigma y plus Cxyy sigma x sigma y cubed. That's the second term. Last term plus Cxxyy sigma x squared sigma y squared. So you see in this formula, we have rho squared here, rho here, and the remaining terms are based on those C something, and that's the covariance actually. So here where this Cxxxx is essentially the covariance of x minus mu x squared and sorry, I should say variance. That's a typo. Variance of this. And what is CXXYY? That's essentially the covariance of x minus mu x squared, y minus mu y squared. By the same convention, we can have xx, xy, this as the covariance of x minus mu x squared, x minus mu x, y minus mu y. So after those algebra simplification, we can basically summarize the asymptotic variance term of sample correlation coefficient as follows. So it's basically depending on the moments of the distribution, the joint distribution of x and y. That will determine those things, and also the Pearson correlation square. So you see that for different values of rho, we can have different gamma square. That would actually decide the asymptotic variance of the sample correlation. If the rho is 0, then we're only left with the last term. That will be the only term remaining in the asymptotic variance. Okay, it looks complicated, right? But this formula can become extremely simple if we assume xi and yi follows from a bivariate normal distribution. So special case. Okay, special case is that if my xi, yi, riid from bivariate normal with mean 0 and the covariance matrix as sigma x squared, sigma y squared, rho sigma x sigma y, rho sigma x sigma y. Okay, if that's the case, you see the way I write it, I actually incorporated the population correlation into the covariance matrix. So if that's the case, then gamma squared becomes extremely easy or extremely simple. We can do the calculation and found that the gamma squared turns out to be 1 minus rho squared. And that's very interesting because it suggests that now it has nothing to do with the moments, just the Pearson correlation itself. And that's a special property of Gaussian or bivariate normal distribution. So again, so this suggests that I would have root n times r minus rho converge in law to normal distribution mean 0, variance matrix 1 minus rho squared. That's it. And then you can see when rho is 0, my variance term is equal to 1, right? And if rho is positive, if rho is non-zero, then rho squared is positive. Then this variance term is getting smaller. So I'm doing better. And so the R will have a smaller variance for a larger absolute value of rho. So you can see that this insight is that if this absolute value of rho is large, then 1 minus rho squared is small. So then my sample level statistic will be more concentrated around the population parameter. It's easier to estimate. And the variance is largest if my rho is 0. And you can imagine that from seeing the scatter plot, actually. Okay, so that's all I want to say about the sample correlation part. Now let's move on to discuss some interesting applications of the asymptotics. How are we going to apply it? So the first thing I'm going to say is that we often involve some unknown parameters in the use of it, right? So for example, let's look at this one. I think this is not a good example. We're going to revisit it, but probably a better example is this. Okay, so recall. So recall our example 3, which we just showed you briefly. That is, we derive the asymptotic, this one, minus sigma square, converge in law to normal distribution mu fourth minus sigma fourth. If you recall, we have derived this. The asymptotic distribution of sample variance. That's from our example 3, right here. This is what we derived last lecture. Okay, so we're just repeating this result. So, but if you're interested in building a confidence interval, okay, so if you are interested a confidence interval of sigma squared, right? That's your parameter of interest. And you want to build a confidence interval based on that. How would you do it? So one thing we are going to take a look at is that we need to deal with those unknown parameters. Okay, so if we do it, we can actually move this variance term to the left-hand side. So the right-hand side becomes standard normal. That's a standard practice. So what we do is that root n Sn squared minus sigma squared divided by square root of mu4 minus sigma fourth. This one converge in law to standard normal, right? Then the way we build a confidence interval is to find the interval that covers 95% probability in this normal distribution. And we call those two critical values. This is a standard practice, right? A standard normal. And we call that this value, if this is alpha over 2, then we call this corresponding quantile as z alpha over 2. And then on the left-hand side, by symmetry, negative z alpha over 2. These two are the two critical values we use to build confidence intervals. So in other words, given here, we can say that this thing, the probability that this quantity is between negative z alpha over 2 and z alpha over 2, this probability is 1 minus alpha. Okay, and then we want to do some algebra to leave just sigma squared in the middle, and we move anything else to the two right-hand side. So we can actually find that it becomes this. So by some algebra, this is equal to that my sigma squared is in the middle, but the left-hand side becomes sx squared divided by 1 plus root n here. And here I would have top one is actually mu 4 over sigma fourth. Okay, this ratio minus 1. That's here. And also z alpha over 2. Okay, that's on the left-hand side. On the right-hand side is almost the same, but change the sign. Sx squared, 1 minus this mu 4 over sigma to the power 4 minus 1 over root n times z alpha over 2. Okay, so you see, what I want is to say that this is the confidence interval for sigma squared. But this confidence interval is not usable because mu4 is unknown, sigma fourth is unknown, right? These two things cannot be known. So, but mu4 over sigma 4 is unknown. So a common practice is to replace this by their estimates. And this is called a procedure called plug-in. So then we do plug-in. That is, replace mu4 over sigma fourth by their estimates. And here we can estimate each of them, right? Mu4 by our previous example is actually the fourth moment, okay? So here we can do that calculations 1 over n summation xi fourth. That can estimate mu4. And sigma fourth itself can be estimated by Sn fourth, right? We use Sn squared to estimate sigma squared. So that's the practical approach. But I think you are aware that this is not perfect, right? Because in statistics, we always concern about the uncertainty in our estimates. And since otherwise we would just use Sn squared to replace sigma squared, we don't need to worry about its uncertainty. This whole discussion about asymptotic distribution and the confidence interval as a result are concerning the uncertainty in Sn squared. But now when we do the plug-in, we ignore the uncertainty at this level. So that's why you see statistics is always some compromise. It's not perfect, right? You're making some compromise here and there. So that's the plug-in approach. Clearly not perfect, but practically that's what people do. Often that's the only option you have. Okay, so, but a better option is not to do plug-in, but try to stabilize the asymptotic distribution so that it's not involving unknown parameters. Okay, so sometimes we could do better. And that is what we call variance stabilizing transformations. Okay, so we're going to use that we're going to use that binormal special case of sample correlation distribution as an example. So if you recall, we have this root m r minus rho converge in law to normal 0 mean 1 minus rho square square. This is what we just derived. And here we also have the same issue. The right-hand side includes the unknown parameter rho. And how do we deal with that? So here we are going to apply Crammers Theorem to help us. So here, by Crammers Theorem, what we are going to do is to do transformation on R. So let's say that we have a function g that maps from R to R, okay? And we want to say that by the theorem, we have gr minus g mu, g rho, convergent law to normal distribution mean 0. And this part would become g prime rho square times 1 minus rho square square. Our goal is very easy. We want to find the g such that this term is no longer related to rho. Find g such that g prime rho square times 1 minus rho square square is not related to rho. That's our goal. And that's kind of straightforward because we can set this term to be 1. Okay, so setting this term to be 1, we actually get that G prime rho is 1 over 1 minus rho squared. And now it becomes a calculus problem. Given we know G prime rho is this, what is G rho? We do integration, right? So then we can get G rho by integrating 1 over 1 minus rho squared d rho. And here is an interesting trick that we may use, right? So 1 over 1 minus rho squared is equal to 1 over 1 minus rho plus 1 over 1 plus rho. So that can make the integration much easier, and divide by 2 for it. So 1 over 1 minus rho plus 1 over 1 plus rho d rho. And then we can easily do the integration. It gave us log 1 plus rho, 1 minus rho. That will be the transformation. So with this, then we can find the variance-stabilized asymptotics. So then we will have root n 1/2 log 1 plus r, 1 minus r. That's the GR minus 1/2 log 1 plus rho, 1 minus rho. Convert in law to standard normal. Now, finally, the right-hand side, the distribution is not related to unknown parameters. This is just related to, this is just the standard normal. And often in statistics, we call this kind of thing, we give a name. This is not in our notes, but I want to mention it. So we call this kind of statistics as pivotal statistics. So the reason is that their distribution is not depending on unknown parameters. The T statistic is another example. Its distribution, the T distribution, is only depending on the degrees of freedom. It's not related to unknown parameters. So these are very useful cases. Okay, so that concludes my discussion about the sample correlation and the functions of sample moments.
So, hi, Professor. Could you explain, like, what would be the application of this, like, the transformation of the sample correlation?
It's still the confidence interval. So here you are going to build confidence interval, not directly for rho, but for this transform rho. So that will be the, you will have, so here, when you build that upper bound and lower bound as a confidence interval for this, the upper bound and lower bound will only involve this thing, only involve R and the critical values. It will not involve unknown parameters.
And do I transform back? Okay, sorry, go ahead.
Yeah, you can do that, right? That's the next step. So okay. So then it depends on whether this is a monotone function of mu or not. So depending on that, after you transform it back, the confidence interval may stay as one interval, or it may be split as two intervals.
Okay, I see. Thank you.
Professor, I have a question.
Yeah.
So
I would suggest that for those of you who ask questions, please show your face. I think that will make it easier. Otherwise, I don't know who is speaking. And to be honest, I feel it's kind of scary to me because sometimes a voice just appear without any notice. That's kind of scary. Yeah.
So we use this to estimate the confidence interval for rho?
Yes.
But why is the original form square root of n r minus rho? This is not applicable.
I would say in this special case, it could be, right? But if you want to do that, you need to divide this to this left-hand side anyway, and you still need to do some algebra to make it so you still need to do some algebra to make the upper bound and lower bound not related to rho. That's the ultimate goal. But this may not be the only way, but it's good to know. I just want to say that.
I see.
Yeah, and also in the old days, so maybe I should mention that in the nowadays, this may not be as important as before, but in the old days, if you recall, when you guys took the undergraduate introductory courses, most textbooks still have that normal table. In that case, it's very useful because in the old days, we do not have computer, and when we look up the p-values, etc., we rely on those few tables in the textbook. So everything we need to convert it to standard normal, so then you can easily look up the table. So that's another reason why it was very useful before. But yeah, nowadays, like I said, you can start from here, you construct a confidence interval and do some manipulation to make the two boundaries not related to rho. You can do that as well. Does that answer your question?
Yes, thank you.
Okay, thank you. Okay, all right, so we conclude our discussion about sample functions of sample moments. I think this is the most critical application of central limit theorem to real statistics. Okay, now we're going to move on to another topic, which is very interesting by itself, but it's quite different from what we have discussed already. So this one is not really about, I would say it's not really about average anymore. Sample moments are anyway averages. Here we're going to talk about order statistics and quantiles. So in other words, this family of statistics called order statistics, they rely on order, right? So an ordering is a different operation, different from averaging. So that's why the properties of order statistics are quite different from sample moments. So I would put order statistics and quantiles together, because these two things are quite related. Sample quantiles are also relying on ordering of the random variables. So here, let's say that we have random variables x1 to xn, and we order them. So, or you can say it's a sort operation. So, and then we sort them from the smallest to the largest. Okay, and then we use the sub-index with braces to indicate that they are the orders, not the original index. So one thing I want to make a note is that in order statistics, everything depends on n. So we first have n random variables, then we sort, right? So the sorting happens for a fixed n. But we're interested in as n goes to infinity. So that's a quite tricky thing. So there's a sequence in your operations. What happens first is that for any n, you sort them, and then you are imagining what happens as my n go to infinity. So in this case, you can imagine that triangular array we saw before, that presentation is helpful. So you can see that we have x1, and we have x1, x2, x1, x2, x3, x1, x2, xn, and so on. So in this triangular array, we actually do sorting row by row. So this becomes x1, x1, x2. And what I want to make a note is that this x1 may not be the same as this x1, because when it's by itself, it must be x1, right? x1 with bracket or not is the same. But when you have x2, then the minimum could be x2. So that's why these two things do not necessarily be the same. And same here, x1, x2, x3. So these two things may not be the same as before. And x1, x2, to xn, and so on. So what I'm saying is that when we do the sorting, it's given a fixed n. but we're interested in the behavior of a statistic as n goes to infinity. So for example, I might be interested in the x1. But this x1 may not be the same x1. So it's changing. That's the thing I want to make you aware. So that's why in the notes, we said that a more rigorous way to write it, but it's kind of complicated. So I would say the more rigorous way to write it is to carry n with it. So we should write this as x1, 1. This as x1, 2. x2, 2, 2, 2, 2. Okay, here it will be x1n, x2m, 2xnn. So a more rigorous way is that we should carry the sample size n with it. So then we can see, okay, these things are not exactly the same because it depends on the sample size n here or the number of random variables in here. But for simplicity, most textbooks use this notation. This one is very rare, but I want you to be aware of that. Okay, the first order statistic we're going to discuss is what we call extreme order statistics. By extreme, we mean the minimum or the maximum. Okay, and the fundamental mathematical fact we're going to use for the asymptotic distribution of these extreme order statistics is this fact. So it's a calculus. It's also from calculus. So all the asymptotics actually has their roots in calculus. So this number, we have n in the power, we have n in the denominator. So you see what's happening very interestingly is that as n goes to infinity, this term, this ratio is going down to 0, right? But there's a power. The power is increasing. So what will be the limit? It's actually exponential. So this is convergent to exponential c as n goes to infinity. This is the fact we are going to use. And furthermore, a more general version of it, is that we can replace n by some sequence that expands as n goes up. And we can also replace c by some sequence that converges to c. So we can write it as 1 over cn over bn to the power bn. This will also converge to e exponential c if cn is convergent to c and bn is divergent to infinity. So if we have those, we still can have this convergence. Okay, that's the fact, the mathematical fact we're going to be based on. But what we're very interested in terms of the asymptotics, right? It's about this. So all the discussion as follows will be of this form. So asymptotics of, let's say, xn. Our goal is to find constant sequences an and bn. Those two sequences such that I would have an multiplying xn, the maximum, minus some bn. My hope is that this is going to convert in law to some x, which follows some non-degenerative distribution. Okay, that's the goal. And here bn could be a constant, right? Constant is a special case of bn. And an, what we know is that it needs to diverge with n. That's some rough ideas we have here. So if you think about the central limit theorem in that form, right, this is the average, and an is root n, bn is mu. That's what we have in the central limit theorem. But here for the extreme order statistic, the maximum, we need to do something different from that because we no longer have central limit theorem to help us. So CLT no longer applies. All right, so what do we do? Let's start from something easy. And we have seen those examples in our undergraduate class, I think. In most mathematical statistics classes, we will use this example. So let's start from the simple thing, x1 to xm, IID from uniform 0 to 1. Okay, that's a very special distribution for these. And then the question is, what is the asymptotic distribution of maximum, of their maximum? So for this case, we will start from the definition of the distribution of xn, the CDF. Okay, so we know that the maximum is a very special thing. If we have the maximum less or equal than t, that's the definition of CDF, right? The probability of that. We know that it implies all the xi's are less than t, less or equal than t. So this is equal to the joint probability that x1 is less or equal than t to xn less or equal than t. And then this is something we can use IID for. Because of the independence, we can factorize the joint probability. Because of identical distribution, each probability is the same. So essentially, this is equal to probability x1 less or equal than t raised to the power n. Then it depends on what t is, right? So we know each of them is between 0 and 1. So then when t is less or equal than 0, it's 0. 0 to the power n, 0. When t is between 0 and 1, is t, the probability is t, and t to the power n. When t is greater or equal than 1, it becomes 1. It stays as 1. So this is the CDF, the exact CDF of this. And what happens, now let's see, what happens when n goes to infinity? Because t is less or equal than 1, then you can see that this CDF, as n goes to infinity, is going to converge to 0 if t is less than 1, and 1 if t is greater or equal than 1. That will be the limit of the CDF. And this is what? This is exactly the CDF corresponding to a point mass at 1, right? This is the CDF of 1. That's the random variable, a point mass at 1. So it means what? So this is actually suggesting, so this tells me that xn is converging in law to 1. And because we know that converging in law to a random, converging in law to a constant is equivalent to converging in probability to a constant, right? We have that. It seems to be good, right? So as n goes to infinity, our maximum will be concentrated on the boundary 1. But this is not so useful, as we said. This is degenerate, right? This is a degenerate limiting distribution, not useful. So what we want is that we want to multiply xn, the maximum, by some divergent constant that increases with n. Hopefully that by multiplying that, we would be able to have the right-hand side not a degenerate distribution. That's the hope. Okay, so now let's revisit this formula. So what about the distribution of this? An times xn minus bn. Would that be better? So now let's take a look. So now we are interested, we change our perspective, interested in the CDF of this, An xn minus bn, interested in this. And we know that with An diverges as n goes to infinity. This is something we know for sure. Okay, so let's do the derivation again. And we can actually, because An and Bn are of our choice, so we can set An to be positive. That will make things a lot easier for us. So we don't need to worry about the sign. Okay, so then you see the CDF of this An xn minus Bn. We call this Ft. Okay, we denote this by Ft. For notation simplicity, it's the probability that An times xn minus Bn less or equal than T. Now you see why I want to set An to be positive. Then I can divide An to the right-hand side without changing the direction of inequality. So this becomes probability xn maximum less or equal than T over An plus Bn. Okay, and then by my same argument, you see, we derived that already, right? So this is actually T over An plus Bn to the power n. If this thing is between 0 and 1. If we have that, then we have this. Okay, and we are actually very, very close. You see, this is the mathematical fact we are going to make use of. So given that, and as I said, An is our choice, Bn is our choice, then why not setting Bn equal to 1, An equal to n? We're done. Okay, so then you can see I can set Bn equal to 1, An equal to n. And then this becomes T over n plus 1 to the power n. The condition should still stay with us if this is between 0 and 1. And then you see I have a limit. This is converging as n goes to infinity. So this CDF is not converging to something like a point mass CDF, but now it's converging to exponential t. Okay? And how can I make sure? How can I make sure this term is between 0 and 1? I have some issue here, actually. So you see that here is that n is this 1, right? So as long as this term is positive, it will not be guaranteed. This will not happen. So the only way to make it happen is to make t negative. Okay? If t is negative, we're good. Okay, that's it. And now you see, this is something we can actually see very interesting. I didn't know if you recall that if we have this, so let's say that we have, suppose we have a random variable following an exponential distribution with parameter 1. So now the knowledge comes into play. If you know this, then you know that the CDF of an exponential distribution takes the form 1 minus, so you know for lambda, that's just for the general case, it's actually equal to 1 minus exponential lambda t. That's the CDF of exponential distribution. So in other words, given this knowledge, then if lambda equals 1, then we would have the probability t less or equal than t equal to 1 minus exponential t. And you see, this is very close to what we have here. It's just that we have e exponential t here, or sorry, I think yeah, that's right. And here we have 1 minus exponential t, right? So yeah, so that's very interesting. I think if I miss anything, I think I missed a minus sign, sorry. Yeah, my bad. Yeah, otherwise it couldn't be correct. Yeah, it's this one. I have a minus sign in the power. That's the exponential CDF. But here we have exponential t. The difference here is that in the exponential distribution, t must be positive, okay? And in our case, we have exponential t, but t being negative. So you see the one-to-one correspondence. It's like this is the left tail, this is like the right tail. So in other words, so given that we have the probability, now an is m, and xm minus 1 less or equal than t, okay, converge to exponential t for t negative, right? What I can do is that I can, so this is on the negative, this is on the, so the domain of this distribution is defined on the negative part of my real line. Now I can take, multiply this by -1 to reverse the sign. Now I come to the positive part. Okay, so then you see if I do the probability of n times, sorry, I forgot this, n times 1 minus the maximum, okay? If I'm going to the positive part of it, and I say that this is greater or equal than negative t, okay? I multiply -1 here, -1 here. Again, you see, this is converging to exponential t, t negative as well, right? It's the same thing. And then furthermore, this implies that if I say the probability 1 minus xn less or equal than, because it's continuous, so I don't need to worry too much about it, less than is convergent to 1 minus exponential t, t negative, okay? Then finally, you see, I can replace negative t by maybe s, okay? So you will see that I would have less than s converge to 1 minus exponential power negative s, s positive. So then finally, we can conclude that this statistic is converging in law to exponential 1. And I'm done. So you see here, we are not using central limit theorem at all. Instead, we were just using the original definition of convergence in law. That is, what does the CDF function converges to? So we're getting the limit of the CDF function and find that it's actually the CDF of exponential 1 distribution. Okay, sorry for running out of time because I didn't notice time when I tried to finish this one. So we'll give you some insights about this next time when we come back on next Tuesday. But this just opens a new topic, and as you can see that it's very different from the central limit theorem and its related sample moments. Okay, so I'll see you on next Tuesday. Bye.